All right. So a few examples of things that are true in Euclidean geometry and why we might care. So let's prove the law of sines. Proving the law of sines is not terribly difficult. We take any triangle ABC and we orient it so that the biggest angle is here, and we orient it so the biggest angle is there so that we can drop an altitude and it lands on the segment to which it is drawn. So this segment has length h. Now we notice that the sine of angle A is this h over that side. That's the side opposite angle B in triangle ABC, so we call it little b. And similarly, the sine of angle B is h over the length of the side opposite A. Well, this means that h on this side is equal to h on this side, and a little bit of algebra tells us that A over sine A is B over sine B. No, nothing special about A and B. A over sine A is B over sine B is C over sine C, and that's the way most of the world learns the law of sines. We can prove the law of cosines in almost as straightforward a way. Here's some triangle ABC. Drop the height to this side, break that up into a y and an x. That's little a, that's little c. So in this proof, we're going to focus on angle C. We're going to recognize that the sine of angle C is opposite over hypotenuse, which means that H is a sinc. And then we're going to recognize that the cosine of angle C is adjacent over hypotenuse, which means that X is a cosc. Now, Y is this whole segment length minus this little piece. Now, we use the Pythagorean theorem on triangle A, B, and we didn't give it a name. And that tells us that y squared plus h squared is c squared. So y squared, b squared plus a squared cosine squared c minus 2ab cosine c plus h squared equals c squared. Now wait just a doggone minute here. Cosine squared c plus sine squared c, that's 1. So this is 1a squared plus b squared minus 2ab cosine c. And the law of cosines is established. Nothing special about focusing on angle C. Could have focused on any other angle. No problem. One more thing I'd like to consider with you. One more thing I think a geometer ought to have in his toolbox. I use this a lot with my math contest writing. So given triangle ABC with D on AB such that angle ACD is congruent to angle BCD, it follows that this side is to this segment of the hypotenuse as this side is to this segment of the hypotenuse. So here's the basic idea here. We draw a line parallel to AC through B. There's only one. There's only one. And that means that these alternate interior angles are congruent, and these alternate interior angles are congruent. Should probably give this 2 swoopies, which means that triangle ACD is similar to triangle BED. And that means that AB is to, nope, that's not true. That means that AC is to AD as BE is to BD. Gosh, we're so close. We're so close. That's the missing piece. But this is BC because triangle BCE has 2 angles that are congruent, so the opposite sides in that triangle are congruent, and so this is BC, and we got it. It's the angle bisector theorem, and because it is based on similar triangles, it absolutely depends on Euclid's parallel postulate. So there are 3 examples of things that you should know how to do. Well, I would expect a student of geometry to be able to fight through and do them. Hope all is well with you and yours. Thanks for watching.